So good morning. We are going to the next week topics, which is killing equations by the syllabus. And it starts with the concept of preservation of length of curves and isometries. So the general topics is killing equations. And we start with preservation of length of curves. So imagine we have a Riemannian manifold. So we are able to compute the length of curves. We have some gamma here from some T1 to T2, and we know that the length of our gamma is given by integral from T1 to T2 dt square root of g gamma dot. Now, if we have a vector field there, some psi in addition, so this psi has some flow, at least infinitesimal, and this flow now can shift the curve to and produce another curve. So we have a manifold. Here is phi t, sorry, maybe it is, yes, it is opposite. Here is phi t, so the curve is here. Is phi t composed with gamma. This is the new curve. So here is somewhere the composition. Goes like that. So now we have two curves, and a priori they have two lengths, different lengths. Yes, so once again, we have original curve. On our manifold, we are able to compute its length. Now we produce, in terms of a vector field, which is given and its flow. We apply the flow on the curve, produce a new curve. Here it is. And we can compute the length of the new curve. So length of this new curve is by definition integral from T1 to T2. And now here should be gamma dot of this new curve. So what is phi t gamma dot? Or in general, what is diffeomorphism composed with gamma dot? Do you remember? It was the definition of something. And this something is push forward. This is the definition of this push forward. So it is not new computation. Push forward was defined exactly in this way. So here we have phi t push forward applied on gamma dot. That means we will have G on 2 push forward like that. Yes. So this is the direct computation that if we have curve and if we apply a flow on it and try to compute what is the new length of the new curve, here is the result. But now there is another definition that if a 0-2 type tensor is computed, evaluated on 2 arguments which are push forwards of something, it is a pullback of G. But on the same on gammas, not on push forward of gammas. So we can write it. Well, first let's finish. d2 dt square root of different metric tensor, or in short that if we have a length, where is the original length? Here we can write it that it is length of gamma on manifold with metric tensor G. So it also depends on G. If you change metric tensor or your manifold, your curves have different lengths. Yes? So the length of the curve parametrically depends on the manifold or on the metric tensor. And this result can be written that if you have the length of phi t gamma on original G, on manifold with a metric tensor G, it is the same like the length of original gamma, but computed on a new Riemannian manifold with new G. So the action on one element of this L, namely gamma, can be somehow shifted on action on the second element, which is just parametrically there. Yes? Maybe I will make a new picture where gamma is in this direction, and here is phi t gamma going this way, the flow. So what is the result? That you can compute the same thing in 2 ways. Either you shift the curve here and compute this new length of the curve, or it is done here on the left-hand side. Or on the right-hand side, you can shift back your pullback, your metric tensor by pullback. So if here were some metric tensor living, now you can pull back it to live here. So here you have now 2 metric tensors, one the original one and one which was pulled back. And you can compute the same, the length of the same curve, namely this gamma, either in terms of the original G or in terms of pullback of G, which came from here. So it looks quite reasonable that if you want to compute the length of the curve which is here, you use metric tensor which is here. So if you pull back the metric tensor here, you are not obliged to go with your curve there, but you can sit on your original place with your curve, but change the metric tensor. Yes? This is the result of this simple computation. That is not necessary to go with curve here. you can pull back metric tensor back and compute the length of the original curve, and you will obtain the length of the new curve. So now, in terms of this fact, we can ask whether they are some mappings which have of the Riemannian manifold, which have this strange property that the length of all curves remain the same. When you apply this f on any curve and you compute the length, you discover that the length is not changed for any curve. So we want such f's that this happens. For any gamma. What is the simple motivation? For example, we have as a Riemannian manifold our plane. Now let's have some curve like that, for example. And we simply made a translation. We translate this curve somewhere. So it is clear that the translated curve has the same length like the original one. And it may be also curved. Translated curve is at another place, but it has clearly the same length in the sense of our Euclidean metric tensor. And do you know some other transformation of the plane which also preserves length of curves in plane? Rotations. Yes, translations and rotations are well-known examples with this property. So what we now want to find is, in a sense, a generalization of rotations and translations of the plane on arbitrary Riemannian manifold. Yes, that what is how we can find the analogues of rotations and translations from the plane to an arbitrary Riemannian manifold, in the sense that the lengths have the same, the lengths of the curves are the same after applying of this transformation. So the best way to do it is to learn that what happens that actually this f gamma g is L of gamma pullback of g, and if this is to be the length of Lg for any L, the best way to do it is find solutions of this equation, that if you do pullback of your metric tensor, it will not change the metric tensor. Yes? In such transformations, it should be transformations of M, that means diffeomorphisms. Such diffeomorphisms of your Riemannian manifold, which have this property, are called isometries. Isometries of Mg. And they can be computed, typically. Now, it is clear from the idea of groups which we introduced some 1 month ago, that here we are preserving some structure. We have a structure on our manifold metric tensor, and we find bijection of M to M, which preserve the structure. So, of course, such mappings will produce some group. If F1 pullback doesn't change a metric tensor and F2 has the same property, then the question is, if we compose these two, is it still an isometry? So we can check it easily because we know how to work with pullbacks. This is F2 star, F1 star by general property of how pullbacks act on composition. Now, this is just G from the first equation, and then this is still G from the second equation. So it is G. So we see that isometries of any Riemannian manifold give you a group. So any Riemannian manifold is associated with some very concrete group of its isometries. And why I started not with F's, but with flows of F's, now the question? Because if we try to find flows of isometries, so this equation says that we have a flow, each member of which is as an isometry. So we have a one parameter family of flows, not just one flow. Yes, and it is a flow. So at phi 0 is identity, and identity is clearly also an isometry. If you do nothing with your curve, you preserve its length. And if you do something and you come back by inverse mapping, clearly if you preserve your length by some f, then going back, clearly you preserve the length. You come to the original curve with original length. So in this way, we have one parameter family of isometries which produce a flow. Now, why this is better than this? Because we know what is Lie derivative. We can just apply d over dt at 0 in this equation. And what we get here, d over dt at 0 from just this part is Lie derivative with respect to the generator, which is called psi. So the left-hand side is this expression, and the right-hand side doesn't depend on t, so it is 0. So we have set, as we will see, set of differential equations, which are called Killing equations. German mathematician Killing found them in 19th century. Now, what we gain if we find solutions, these solutions of this equation? We'll do it in detail, yes, but now just in the beginning. If we find this psi from these equations, we can compute the flow of this psi and has big isometries. Yes. First, small isometries, infinitesimal isometries are given by infinitesimal flow of your vector field. And then by addition, we know how flow behaves, that 1,000 of iteration of 1,000 of very small transformations give you a big transformations. So we will see in detail how it acts, but this is the idea that you can in principle also write down in detail this equation for directly big isometries, but in general there are much more complicated equations like those equations for infinitesimal isometries, actually. Yes? That to find something which is isometry and it is very near unit transformation is, in general, much easier than to find from this equation directly the solutions of any big isometries. Of course, we cannot find any isometries in this way, because there are also isometries which you didn't mention when I asked that, for example, in the plane, once again, if we have some curve like that, can you imagine something which is isometry and it is different from translations and rotations of this curve? We have some curve from A to B, it has some length, and can you imagine some transformation of the plane which makes a new curve with the same length, and it is not rotation and translation, neither rotation nor translation. What it could be? Sorry? Reflection, exactly. So reflection, for example, with respect to this axis, gives you some curve like that, and it is clear that it has the same length. But there are no small reflections. This is the crucial thing, that translations and rotations can be produced out of unity by infinitesimal changes. First, small translation, bigger, and so on. But there is no small reflection, and from small reflections you cannot find the big reflection. Yes? So reflections are out of scope of this method. If you want to find reflections, you have to solve this directly, or check that reflections works for this equation, if you think that reflections is a good idea. So here we restrict to transformations which can be produced from identity smoothly. Yes? And reflections are not of this type. Now, in the same way, like solutions of this equation, that means isometries, form a group, as I checked here, solutions of this equation produce Lie algebra. It is actually Lie algebra of the group. So by finding xi's, we obtain Lie algebra of isometries. And how we can check it? We can check it directly from this equation, that the statement is, if we have two solutions of this equation, so explicitly this is 0 and this is 0, 2. The claim is that the commutator of these vector fields is also solution. So here is also 0. And how we can prove it? This was mentioned on the, I think that at the last lecture, that it is Lie derivative of xi1 and xi2 minus opposite. In order to prove this, we introduce the concept of tensor algebra and derivations of tensor algebra. And so in this ideology of tensor algebra, we proved the fact or the identity, the Lie derivative in the direction of the commutator of two vector fields is commutator of Lie derivatives. Yes? And now, if this is true, if we can replace this by this, so if we act on G, the first guys already give you 0, because this is assumption. So it is quite elementary to prove that here you obtain 0. Actually, you obtain 0 minus 0, but scientists discover that it is 0. Yes? First 0 minus second 0. And also, it is just a commutator, but in Lie algebra you need also the linear combination. But at the same time, when I show that how to prove this, in the same way you can prove the formula that this is L psi 1 plus lambda L psi 2, that Lie derivative in the direction of linear combination is linear combination of Lie derivatives. So acting on G, once again 0 plus 0, again 0. So they produce Lie algebra. Yes, Lie algebra of the group of isometries. So actually, when we solve Killing equations, we obtain Lie algebra of a group of isometries. Now, what the equations look like in detail, how to solve this equation, you have to write down the equations in coordinates and solve them. So what are the equations? Now, we have to write down Lie derivative of metric tensor according to our rules table, that Lie derivative with respect to psi of G, I, J. The first term is psi applied on Gij. This is for any tensor, regardless how many indices it has. And now, for two lower indices, we have some term which you can find from the table. And this should be 0 by Killing equations. And here you can check that it is Ki, Kj, and Kj, I, K, according to the table. And this, in detail, is psi K, Gi, J, comma, K. So we see the details of these partial differential equations. Partial differential equations for psi I x. Yes, we have a system of partial differential equations for unknowns which are components of this vector field. Yes, we find the complete vector field. So in coordinates we try to find its components. But components are functions. So we have n unknown functions to be specified by the equations. Now have a look that this system of equations is, well, first I forgot to tell that they are linear partial differential equations. But still rather complicated. But some properties which we know help very much to solve them. And how many of these equations we have? We know that Gij is GJI. It is symmetric tensor, yes? Now, Lie derivative of J has the same property, check. So, our system of equation is system that Aij equals to Abi, where Aij is something. If you write down this matrix, that means that we should know just this part of the matrix. So there are so many equations as is the number of elements in such a matrix. And this is n times n plus 1 over 2. This is the number of these elements. So this is the number of equations which we should write explicitly. So for example, if we write this equation, we needn't write explicitly this equation because it is already here, the same content. And how many unknowns are? Just n functions. Where is n in this matrix? For example, here. Yes? So what we see that there are more equations than unknowns. Unknowns, I don't claim that here are unknowns, just the number, yes? The number of unknowns is the number of these elements. And the number of equations is the number of those elements, which is bigger. So, we have more equations than unknowns, and it means that it can be not possible to find any solution. Yes? So maybe no solutions. Because there are too many equations for our unknowns. It is overdetermined system. And it often happens, or in some sense, it is typical situation that for arbitrary Riemannian manifold, you have no solutions. But we are, in major cases, interested in not very much arbitrary Riemannian manifold, but Riemannian manifold, which actually have some symmetry, and because of that, typically, for practical point of view of applications of this, we typically have some solutions. Yes? But in some mathematical sense, typically we have no solutions. But from practical point of view, typically we have solutions. What is now the profit from the knowledge that our solutions actually correspond to some Lie algebra? That the Lie algebra structure says us that if we have two solutions, this is also solution, and this is also solution. From each two solutions, you can compute the third and the fourth solution of this structure. Now, this is rather trivial because the system of equations is linear. So for linear equations, this is not very deep knowledge, additional deep knowledge. But this is quite deep knowledge because it is not visible at all. They are linear, these equations, but it is not visible that if you have two solutions and you compute something complicated, which is commutator, it is some combination of these two fields, including differentiation, Yes, because here the components are differentiated, and still it is a solution. It is at all not visible, but we know it from the fact that we know that this set of equations is actually the condition that Lie derivative with respect to psi of g is 0. Yes? So if you see just these equations in components and you do not know the content of these equations, well, you cannot do such effective algorithms to solve it as if you know the content of these equations, that it is solution of equations of finding isometries, and that's why linear combinations commutator should be there, always. And it can be shown, I will not do it, that this number is actually the maximum possible number on n-dimensional manifold, the maximum possible dimension of this Lie algebra. Yes? So this is, at the same time, the number of equations, at the same time, the maximum number of the Lie algebra can be proved. It is not done here, but it is a practical knowledge. So, if we know that the space of solutions is a Lie algebra, it has some dimension, and we know the upper limit of this dimension on n-dimensional manifold, and it is quite useful because, for example, we will find on exercises this Lie algebra for the round sphere, two-dimensional sphere. The sphere is two-dimensional, so here we have 2. We see that this number is then 3. So we know in advance that if we want to find solutions of this set of equations for the sphere, and we already find 3 linearly independent solutions, that there are no other, that we can stop of our trials. Yes, that if you know that how many solutions they are, and you already have this number of solutions, that it is okay because you can stop to find more solutions. There are the manifolds, Riemannian manifolds, which have this maximum number, are, I think, called that manifolds, Riemannian manifolds of maximum symmetry. Yes, that there is already no more possible symmetry like this number of Killing vectors. The solutions are called Killing vectors of these equations. So we are speaking that linear combination of 2 Killing vectors and commutator of Killing vectors. And notice that we speak of vectors, but they are actually vector fields. Yes, that formally okay should be to say that we are trying to find Killing vector fields, but typically it is said that we are trying to find Killing vectors. So now let's do an easy example, at the same time useful, that how to solve these equations in a very simple but illustrative case, and it will be the case of the Euclidean plane. So, as you told me, you know that translations and rotations are there, and actually we will check whether there are also some other isometries, but not this X, for example, this isometry reflection we cannot find because it is not of this type. So our Gij is delta Ij. Ij goes from 1 to 2. Yes, we have coordinates x1 called x and x2 called y, typically. And what we want to find is xi1 x, y, x, or xi x, plus xi y, x, y, derivative with respect to y. We want to find these two functions. The most general solution of Killing equations with this vector field. So first, we have now just 2 by 2 matrix of these equations. This ij goes from 1 to 2. So we should write these 3 equations. So 1, 1 equation, 1, 2 equation, and 2, 2 equation. Notice first that our Gij is constant. Where it is? It is constant. So the first term is not working in our case, not in general, but in our case. Now, this is just 0 because it is derivative of constants. Here we will have, when we compute 1, 1, it is this one and this one, yes? And kk is 1, 1, 2, plus 2, 2. So if here is 1, 1, we will have k, comma 1, g, k, 1 from here, plus psi k again, 1, g, 1, k is 0. But because Gij is delta, so this is delta k1. Also here is delta 1k, so k1. And that means that the sum is just one term, yes, with k equal 1. So we have psi 1, 1, delta 1, 1, which is just 1, plus here again the same. And this should be 0. So I will write the real equation here. This is 1, 1. Now 1, 2, k I1, so here is 1, and here is k2, plus psi k, now 1 is on g, and here is 2. Should be 0. So this is again delta k2. So it will be psi 2, comma 1 plus opposite psi 1, comma 2 is 0. And the third one, you can check that it is exactly like the first one, but with 2 number, yes? So the third one is 2, 2, and 1, 2, and 2, 1 is 1, 2 plus 2, 1 equals 0. So this is our real system to be solved of our 3 Killing equations for the plane. So from here, because comma 1 means derivative with respect to x, we see that psi 1 x y doesn't depend on x. Yes, no x. From here, we see that psi 2 doesn't depend on y. It is just some function of x. Let's call it a y and bx. Now here, this ay is differentiated with respect to this y, plus psi2, that means bx, is differentiated with respect to this x. And added together, they should give us 0, or a primed y is minus b primed x. But now we see that we have a function of just y on the left and function of just x on the right. So here both sides should be a constant. We can separate them. And the same constant, of course. And then we can solve it, that if a primed y is k, a y is ky plus some q1 and minus b is k, so bx is minus kx plus some q2. So we see that the most general solution depends on three constants. And what is our psi? It is psi1, which is a. So this is psi1, and this is psi2. Yes, it is k1 plus q1 with this basis vector plus b, which is psi2, so b is here, minus kx plus psi2 derivative with respect to y. Now we can treat this as a linear combination of some three guys with coefficients k, q1, and q2. So it is k times something plus q1 times something plus q2 times something. And what is this? What are these three somethings? K is y derivative with respect to x minus x derivative with respect to y. q1 is just derivative with respect to x, and here is just derivative with respect to y. So this is a basis of the solution space. The solution space is linear space. It is more than linear space, it's Lie algebra, actually, but a linear space. And here is a basis because this is the most general solution. So we try to understand the result. We have three vector fields, y, x minus x derivative with respect to y, and this and this. They are generators of some flows, as always, Killing vectors. So there is some flow number 1, t, here should be some flow number 2, t, and here should be some flow number 3. We have three independent flows which are isometries. Now, do you remember what is the flow here? That x, y goes to what? And here. That what is the flow generated by partial derivative of x? What are equations? With this vector field, the components are 1, 0. So 1, 0. So what is the result of this flow? Translation. But which translation? X direction. X plus t, y. Here the opposite. X, y plus t. And what here? We know already this vector field. Do you remember what this vector field produces in the plane? We know it with minus sign, this. Rotation. It is rotation. It is minus derivative with respect to phi, if I remember correctly, yes? In polar coordinates. So, in this sense, it is rotation like that. So it can be written some x cosine t and so on. That's a rather long expression. By the way, we could solve this equation directly in r phi coordinates. Yes, that we could try to find r phi, r plus phi, r phi, phi, and g equal, or the matrix of g be 1, 0, 0, r squared, gij, maybe gij equals. You can try to write down these equations. And now, if you write this equation, you will see very quickly that this is a solution. Yes, because we found these solutions in Cartesian coordinates. It looks like that, but we know that it is this. But it is much worse for discovering these translations, because translations in polar coordinates are not very nice. So when you do it, when you try to find solutions of this equation in polar coordinates, you easily found this rotation, but a little bit harder you find translations. If you do it in Cartesian coordinates, translations are easier than rotations a little bit. But in Cartesian coordinates, as we see, it is so easy that practically you find directly everything. Yes, because it is very easy. So now we see that that here is the basis of solution, and each basis has some meaning, that it produces some basic one parameter family of isometries. Yes? So if you have, for example, Q1, this solution, and K1, this solution, plus K2, the second one, for example, if psi is this, what is the flow of this? What do you think? That what flow is produced by this linear combination if we know that the basis produces flows like that? Can you give some hint? Maybe it will be not okay, but what do you think by intuition? First, what happens with if we will have just k times this vector field? What changes here? This is with just this basis, and what changes? Here you have solutions or equations for the flow, and if we have k times this, what is different in this system of equations? that instead of what you have what. This is 1 derivative x plus 0 derivative y. Yes? Here. So what should be there? K. Here is k. What is the result then? Where is k there? Plus kt. Okay. And what happens if you have this linear combination then on the flow? That it is this and this all together. So, and what is it? In plain English, not plain Slovak. It is a translation in general direction. Yes? Now, rather complicated thing, what about the linear combinations of all three? It is something which is combined from translations and rotation. Now, notice that this rotation, each rotation has some center, the center around which rotation is produced. What is the center for a rotation given by this vector field? Which point is the center of rotation? Yes, this one, yes. So, this field produces rotation around this. Now there is a nice example or exercise, very simple, that what happens if you have combination of all three, that if you make a new choice of coordinates which is just shift, so here is x, y, and here is x primed, y primed, just shift it, not rotate it, yes, shift it. By general shift, that some A1 here and A2. If you write down linear combinations with three different constants of this, you can adjust your shift in such a way that you can kill this translational part. So it will be a pure rotation, but around this point. Yes? I don't know where is the exercise. I can write it 4, 6, 8. Yes, this is 4, 6, 8. Very simple exercise at the level of Lie algebra, not at the level of rotations of the big transformations, but at the level of generators. You can discover that if you have real linear combination of all these three vector fields with non-zero coefficient here, that means there is some rotation there in this linear combination, then you can shift coordinates, and in new coordinates you will have just pure rotation. Pure rotation means that y primed, x primed minus x primed, y primed. Yes? And nothing more. Yes? No this primed and this primed. You can adjust A1, A2 into it. So it is some knowledge from elementary geometry that if you have a combination of translation and rotation around some point, actually it is a rotation around different point. Yes? So it looks in original coordinates, the complete flow can look rather complicated. What is easy is pure translation in arbitrary direction and pure rotation around the origin. But in general, it looks complicated. You don't know what is it. But after some shift, you know that, oh, it is just rotation, but around different center. Yes? Okay. So this was an example. And I wanted to tell that, going back, that the fact that commutator is a solution is very non-trivial knowledge for solving this equation. You can proceed as follows: that we know that the maximum number of solutions is this one. sometimes you can find solutions by guessing, yes? That because of this situation, I guess that this and this should be solution. You can insert it as an ansatz, and it will become true, simply, that this is a solution. And now, imagine that you have two such good ideas, that you guess two solutions. Then you can compute a commutator. You obtain third solution by some good idea, not by guess. And this solution can be something which you cannot guess. But you have already third solution. Now, if you have three solutions, you can produce commutator of the third one with first, third one with second. You can maybe construct other solutions. Yes, so this fact that this is also a solution is very non-trivial, and it is, as I already told, it is not just trivial thing that it is a linear equation, so we can linearly combine. It is very non-trivial operation, this commutator, for solving this operation. When it does not help, sometimes this commutator is zero, then nothing interesting comes. Sometimes it is linear combination of xi1 and xi2 and nothing more. In this case, you do not find interesting new solutions. So it is not always true that it can help you. Yes? But sometimes it can help a lot to find the third solution, and then by further commutator to find maybe the full number in optimal situation. Now, some more examples. I will not do all solutions, but ideas from interesting examples which are in the book. For example, you remember that there is torus embedded in E4. You remember that when we studied induced metric tensor, we induced metric tensor on torus from E4. Also from E3, it is standard torus in E3. But there is interesting torus which with metric tensor embedded from E4. And it came to be very simple. So its matrix is like that. In the plane of alpha and beta, it is exactly like in E2 alpha beta. But it is globally, it is not E2 because there is periodicity with respect to alpha and beta, recall. Yes? That this point is same that this point and this point and this point and so on. There is a infinite periodicity. So actually, these are points from our T2, and all other points of our alpha-beta plane are just a repetition of these points. Now, if we try to find Killing vectors of this situation, of this torus, because it is a Riemannian manifold, what we find? It is the same like we did already, yes? Because the metric tensor is the same. So we have three solutions. This, and beta alpha minus alpha derivative with respect to beta. what are the flows? For example, flow of alpha is this one. And there is no problem of this repetition, because this repetition means that we can identify these two sides physically. So if the flow which looks like that in the alpha beta infinite plane is actually a flow around some cylinder, so to speak. But there is also this identification, but now we study only this flow, and it has no problems. You can think it over. Yes? That this is good, but this is bad. Can you tell me some reason why this is bad? What this flow does? It does rotations around this point. What is bad on this vector field? Interpret it as a vector field on the torus. It is psi alpha beta, and this is, or with minus, this psi beta alpha beta. Yes, it is by definition. And our psi alpha is beta, and our psi beta is minus alpha. But this should be always possible. And if you do it on these components, you see that it is not too much okay. Yes? So these two functions are not periodic. If you want to have a vector field which is defined on this torus, in order to be just continuous, you need periodicity in alpha and beta. And these functions are not periodic in alpha and beta. So this is not well defined, simply. It makes no sense, directly speaking. Yes? This is not a vector field on our torus, in this model of the torus. So we see that what happens sometimes, that what we actually compute from Killing equations we find the Lie algebra of local isometries. But that means that, well, they are differential equations, so they compute something just locally, first in coordinates, yes, and they do not see the whole manifold in one set of coordinates, at least. So, for example, in this case, for the plane, it is okay, but now, taking into account that we have no just plane, topologically, the manifold is more complicated. So, local isometries, which we are not interested in the topological structure of your manifold, can occur which are not isometries of the global manifold. Yes, they are isometries of small piece of the manifold. For example, you can make translations here. It is not a problem, but also rotations, for example, around this, inside the square, but not rotations with the whole manifold in this sense. So sometimes when you find all Killing vectors, you can be careful whether all Killing vectors are compatible with the global structure of your manifold. And if not, then simply pull them out. And the Lie algebra of real isometries of your manifold can be just some sub-algebra. You can check that you have some three-dimensional Lie algebra where this is the basis, but this is the basis of some two-dimensional subalgebra, Lie subalgebra of the complete three-dimensional Lie algebra, which is not interesting. What is really interesting for this manifold is just this subalgebra. They are good operations there. Now, the interesting situation is on manifolds which are created by rotating of some curve. We had some exercise like that if this is Z and this is some R on Z, we can have Z and phi coordinates on rotational invariant surface. By rotation of this curve around this line, we obtain some rotating surface. And now imagine that we have a curve here, this gamma, and if we rotate this manifold around the z-axis, this curve comes here. But because it is a rotation, it is clear that the length of the curve is the same. Yes? So the rotations around z should be isometries of this surface, independent of the particular curve. Rotations around z for any rotational surface should be isometry. It comes from our logic and understanding of the situation. So what is the generator in these coordinates? The generator is this one of the rotations around z, because phi is defined in this way. So this should be z phi z plus psi phi z phi phi. So this should be 0 and this should be 1, maybe some constant. So if you write Killing equations for this case, for rotational surface, you know from the very beginning that this should be a solution of this equation. And you can check that it is really the case. There is an exercise, where is it? Somewhere, yes. 469. This. It is not so much important as particularly this case, but the idea is important, that sometimes you can guess solutions of Killing equations, but just having a look what we are speaking about. For example, if you have, once again, also rotation surface is what is, I think that this is the right picture, not very much, maybe this one. So torus T2 in E3. It has more complicated metric tensor, which was computed sometimes. Here we have some parameters A and some B inside. Yes, but rotation of A and B, by rotation of A and B, you produce the torus. There are some formulas that X as a function of psi and phi, and Y psi phi, and Z psi phi, so on. And from this, you can compute induced metric tensor, which will be something. Yes, it is somewhere in chapter 3. It is a rather complicated metric tensor. So when you set the equations to be solved as Killing equations, they produce not so easy set of equations, because the situation is not so easy. But you directly see, once again, that if phi is this angle, this should be a killing for your system of equations. So there are maximum 3 solutions because it is 2-dimensional. And one of them you just see. You can check. I think that there are no other killings. I don't remember exactly, but it seems to me that this is just one-dimensional space of solutions there. For example, if you try this, this produces what? It is some turning around this torus, but in this way. And you can see that it cannot be a solution because the length of some small curve gets bigger and smaller if you go around. Yes? So the length is not preserved by that. But if you take any curve here and rotate it around in this way around the torus, it will be still the same. So you see, directly from what is doing, you can imagine that can this flow be an isometry? Not because something gets bigger and smaller, so it cannot be isometry. For example, this one, yes, it's not isometry. And also interesting situation comes on a standard sphere. When you have a look on the sphere, you see that it is rotational invariant. But if we use theta phi coordinates on the sphere, as usual, so for example, we see that this will be solution and this will be not a solution, because what is flow of this vector field? It is going around, along meridians, and if you have such a line here, and the flow of this line will be here, now the result of the flow, and this is longer than here, yes? So the lengths are not preserved by flow along meridians, but the flow along this for example, along equator and so on, is okay. Yes, the rotation around that axis. So the problem with solution of Killing equations, which are quite complicated, is that not all rotations are clearly solutions. We know it. We have a look and we know it, that rotations of the sphere preserve any length of curves. But the problem is that all rotations are not nicely described in these coordinates. So these coordinates are not adjusted to rotations which are not rotations around that axis. If you imagine the rotation around or about x-axis and try to write down this rotation by angle alpha in coordinates theta phi, it is very cumbersome, this formula. So you probably will not discover them by just writing the solution. But you can discover them by solution of Killing equations. So it is, of course, some exercise that try to find isometries, that means to solve equations for the sphere. Where is it? I don't see it here, but somewhere it is here. Yes, 4, 6, 11 is the sphere. And if you write down the set of equations, then you can do some manipulations with the set of equations and finally to solve it. You can find the general solution. And it has actually 3 parts. Arbitrary. So, after some struggle with the set of equations, which is much bigger than our struggle with our very simple Killing equations for the plane, but it is at the same time quite doable. You can do it as a homework and show us what to do with equations. You find that, for example, here will be this guy, but these 2 guys are complicated. This is extremely simple, and they are rather complicated, but can be found. So what is the interpretation of these 2? We know what is the interpretation of this one. This is rotation around z-axis, so it is very probable that this is some linear combination around of rotations around x and y. So there in the hint is the first, well, do it yourself and try to find this, and the second second part of the hint is that at the same time it can be given by completely different method, that we know that solutions should be rotations. So take the rotations first in the whole E3. In E3 with standard coordinates x, y, z. For example, z rotation, we know that it is minus yx plus x y. This is rotations around or about z. And similar expressions, for example, about x is what? Z is there, so x is z y plus y z, and so this is x y z. Here will be minus z x plus x derivative with respect to x. So these are, by the way, Killing equations. There are 3 Killing equations of 6 possible in E3. In E3, what are the Killings? 3 rotations and 3 translations, altogether 6. Yes? It is 3-dimensional manifold. So it has also maximum number of symmetries, this E3. En has maximum number in general. And now, how can we get solutions for the sphere from this? We can use r theta phi instead of x, y, z. So we know solutions in Cartesian coordinates. We can rewrite them. It's not very pleasant computation, but it is mechanical one. Rewrite these solutions in the language of r theta phi. You will see interesting phenomenon that there is no r coordinate in any of them. Yes? So all these 3 guys have just theta phi and derivatives with respect to theta phi's. And what they are doing, they are doing the rotations of the whole space. But if we just fix it for r equal 1, which is our sphere, we obtain the solutions in the language of theta phi on the sphere. So this is the possibility to do that and to understand these 2 solutions, that these 2 solutions will be there in your solution and in the new solution, yes? That rewriting these well-known 3 fields to these spherical polar coordinates, and then have a look that one of them is very simple. This is This is derivative with respect to phi. Two of them are complicated, and they are just in the language of theta phi, there is no r. So you can restrict it to your sphere, putting r equals 1. You will see that it is no place to do it. But you simply think it that now I put r equal 1. Well, nowhere possible. Never mind. I already did the work. I put it r equal 1. So the expressions, which will be in these two coordinates, one of them is here, and two other possibilities are there for that, and they are generators of rotation of our sphere around x and around y. Yes? So one can understand fully these Killing equations and solutions and all that, these isometries of the sphere in this way, through Cartesian coordinates in the bigger space. And now I will just start, and I will finish it next time. That what about very interesting and important situation for physics? Or PQ. So pseudo-Euclidean space. It is interesting case is En and E1n. Actually, yes. In particular, this and this. These are the most important cases. But we can do it for general RS and analyze it. So what is Gij in Cartesian coordinates? It is eta ij now. But still constant. This is important. Eta ij are constants. So what happens with our system of Killing equations? First, this term is 0 because it is derivative of constants. So know this term. And also here happens something interesting. Ki eta kj plus psi kj and eta ik is 0 now. And notice that here one can do something which is not possible to do here, that put this eta under this comma, that we can write it in this way. Comma j. This is not possible here because differentiation of g is non-trivial. Now what is this? It is just psi j, and what is this? Is psi I. So the last line from which I will start next time is that we have set of equations psi j I plus psi I j equal to 0. And psi I is eta I j psi j. So actually we will solve the equations not for Killing vectors but for Killing covectors. These are components of covector assigned by G to our vector. Yes? We first find solution of components of Killing covectors, then raise the index trivially, and we will have components of Killing vectors, and we will try to understand them. But this set of equations has such structure that it can be nicely solved to the very end and to understand the solutions completely. I will do it next time. Thank you.